All right, guys. We're just continuing our practice final exam for Chemistry 1. Um, we've done questions 1 through 15 on the practice final, and we're just going to continue moving on. So this is question 16. Um, when we look at the test, we have here we have a potential energy diagram. Before we even read the question, remember what these tell us, right? This is the reactants, this is the products, but that's if we're talking about the forward reaction. If we have a reversible reaction, the reverse reaction, we could read it from right to left, and that would be the reactants of the reverse reaction, and over here would be the products of the reverse reaction. So the first thing we should notice is that the forward reaction gained energy, so that's endothermic. So we know the forward reaction is endothermic, that would mean the reverse reaction is exothermic, okay? And remember, if we want to know the delta H, the enthalpy change or the heat change, which they're asking for in question 16, enthalpy change, remember that's delta H. Remember, you can think of that as the heat change, the energy change of the reaction. And the energy change is this much, right? This is the start, this is the finish, and that difference, energy difference there is the change. So we're at here at around 350, and down here is 150. So the difference is 200 kilojoules. Now, because it was a gain of energy, it should be the positive 200 kilojoules. If it was the reverse reaction they were talking about, now we would say exothermic, and it would be a negative 200 kilojoules. Okay. But yeah, the answer is C. It's endothermic, the forward reaction, and the delta H is 200 kilojoules. Okay, so remember, you can always get the delta H this way when we're talking about this reaction, this chart as is, because the products are higher in energy than the reactants, the delta H is positive. But if the products were down here and the reactants were up here, that would be an exothermic process, but the delta would still be the same number, right? Okay, so hopefully that makes sense. All right. So here we're given a sodium hydroxide solution. We're told the molarity of hydroxide, and we want to know the pOH and the pH. So this one sets us up. It doesn't try to trick us at all. But understand, like on the actual exam, on the final exam, you might be given this solution and just ask for the pH. And so what you got to remember is if you know the hydroxide concentration molarity, you can get the pOH. The negative log of this number is going to be the pOH. But to get the pH, you have to remember that pH plus pOH always adds up to 14. And remember, these are on your formula sheet. So let's find them, right? So right down here, we have our acid-base equations. So we have the information here to calculate the pOH. And then we have to, once we have the pOH, 14 minus the pOH will give us the pH. Okay, so it's going to be a basic solution. So it's going to have a low pOH or a high pH relative to 7, right? So we take the negative log of 0.005, and that comes out to be 2.3. So the pOH is 2.3, and then 14 minus 2.3 gives us the pH, and that's 11.7. So that's our correct answer. Okay. All right, moving on, we're taking a measurement. Just remember, you need one estimated digit. So each calibration counts one, I guess, centimeter. And so we need to estimate to the tenths place. So, you know it's more than 9 and you know it's less than 10. So obviously 10 and 9 wouldn't be right. But we don't have the precision enough to say 9.75. We only have the precision to estimate to the tenths place, right? So the tick mark gives us the ones place. We estimate to the tenths place. If we had smaller tick marks here that represented, maybe 0.1 centimeters, then we could estimate to the hundredths place, right? But because each calibration mark, each graduation, counts as 1 here, that's the ones place where we need our estimated digit at the tenths place. All right, so our correct answer should be 9.7. And this would be one where you could process of elimination it. You need 1 decimal place and that's it. So that had to be the answer. Okay. Moving on here. So naming our are just finding the type of compound, so covalent. So we can't have any metals, right? Or ammonium. If you had NH4 as the start, you know that's ionic, right? So sodium sulfide, that would be ionic. Calcium oxide, ionic because calcium and sodium are metals. Lead 2 sulfate, that would be ionic again because of lead, right? So these are all ionic compounds. Remember, organic compounds are covalent. So this is organic, but remember, organic's just a subcategory. It's a really big category, but it's a subcategory of just covalent compounds, right? Non-metals, that's what you're looking for, okay? But don't get fooled by ammonium. Like if you see NH4Cl, those are all non-metals, but that would be ammonium chloride and it would be an ionic compound. But remember, ionic compounds can also have covalent bonding. Like this ionic compound has covalent bonding between the sulfur and the oxygen, right? So if you have a polyatomic ion that's made up of non-metals, there's covalent bonding between those two atoms, but we still call this a salt or an ionic compound, okay? All right, so here we want to find electron configuration, and this is where we just have to be careful, right? So if it was P, the correct answer would be A, right? 1s2, 2s2, 2p6, 3s2, 3p3, because that's where phosphorus is on the periodic table, right? So let's go to the periodic table and remind ourselves electron configuration, right? 1 s block, 2 s block, 2 p block 6, 3 s block 2, and then 3p block 1, 2, 3, right? So 3p3. But that's if it was p neutral, right? But this was p3 minus. So remember, 3 minus means I've gained 3 electrons, so move 3 spaces to the right. It's going to be argon's electron configuration, right? So remember, that's why phosphorus becomes a 3 minus ion, because it fills its octet, right? So this is normal phosphorus, but remember that 3 minus means 3 more electrons. Where do they go? Remember, the p sublevel can hold 6 electrons. Right now it has 3. Those 3 more electrons go there. So now you have argon's electron configuration, okay? And remember, especially at this level right now, if you're asked an electron configuration question, if it's an element, it's just, you know, the normal neutral. It's just its normal electron configuration, the way we know how to do it. But if it's of an element that's in a compound, remember, in a compound, right, they've transferred electrons, they've shared electrons, so now they have a new electron configuration. So if it's in a compound, it's always going to be, you know, the same electron configuration as, you know, the closest noble gas. So if it's phosphorus neutral, I know to stop here in my electron configuration, right? But if it's phosphorus in a compound or phosphide 3 minus, I go to here, right? I go to argon, which is phosphorus's closest noble gas, right? Calcium 2 plus, if it was calcium 2 plus, it's going to be argon, right? Because 2 plus means I lost 2 electrons. Okay. All right, back to the test. All right, so this one is, you know, can be kind of complicated because it's limiting reactant stoichiometry, and so you just have to like count and do all the different things, right? So this is the balanced equation, and what we have to take from this is if we lose 1 aluminum, we're going to lose 3 silver ions, right? So for every 1 of these that gets used in the reaction, 3 of these gets used. And then for every 1 of these that we lose, we gain 1 of these, and we gain 3 of those, right? So let's look. In this beaker, we started with 4 aluminum atoms, and then after the reaction goes to completion, we're left with 2. So we lost 2 aluminums. So that means 2 aluminums reacted. Okay, so if 2 aluminums reacted, how many silver ions reacted? So if 2 aluminums reacted, 6, right? 6 silver ions reacted. So in our drawing over here, we got to get rid of 6 of these, right? So we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 of them. So we should have 2 of these ions left over here, okay? But then we have to have our products. So we lost 2 aluminum atoms, so we're going to have 2 aluminum ions over here floating in solution. And we're going to gain 6 silvers. Now it's silver solid, so you would stack up kind of the silver atoms the same way the aluminum stacked over here, but you would stack up 6 of them. And so that's what would be in your beaker. And then I don't want to read it. And this is the right answer. So on the right side, we should have 2 silver ions left over. We should have 6 silver atoms. Those are my silver atoms stacked up over here. And 2 aluminum ions, aluminum ion, silver ion, silver ion. Now, if we wanted to be really accurate about it, the silver atoms, these spheres, should all be bigger than those spheres, because when that silver ion gains an electron, it ends up with a bigger radius. And then the aluminum ion sphere should be really small compared to this sphere, because it lost 3 electrons. So its electron cloud would be a lot smaller. So really the aluminum ions here should be much smaller, right? But that's not, that's just a little extra detail that we really don't need. It was just really about, hey, can you like read the recipe and know how much stuff am I going to lose? How much stuff am I going to gain? What will my beaker look like, afterwards? Okay, so for this one, it came out to be B. All right, so we keep on moving. All right, so we have an empirical formula and we have a molar mass of a compound. Okay, so what's the molecular formula? So all we have to do is find the molar mass of this and then take the molar mass of the compound divided by the molar mass of the empirical formula. That's going to come out to be a whole number, and whatever it comes out to be, you multiply your subscripts by that, and that'll be your formula. Now we could probably maybe process of elimination, see if any of these choices don't reduce back to this ratio. It looks like they all do reduce back, so I guess each one of these could be a possibility. So the other way you could do it is just like add this up and see if it's 172, and if it's not, add this up and see if it's 172, and whichever one of these adds up to 172 is going to be your answer. Okay, so when we add this up, this comes out to be around 43. So if we do 172 divided by 43, we get 4, and then so we just have to multiply our subscripts by 4, and we get our molecular formula. Okay. All right. All right, so in the next one, it says selenium. Okay, so let's find it on the periodic table. It's here. Okay, so 6A, it has a total of 34 electrons when it's neutral, and it has 6 valence electrons. So let's go to, so in a dot structure, it would have 6 dots, because remember those represent the valence electrons, and 2 of the electrons would be it would really be, I have this switched, so sorry, the key's wrong. It should be 4 electrons are paired and 2 electrons would be alone. So this is what it would look like, and hold on. So it should be, did I read that wrong? Selenium would have 6 dots. 2 electrons would be paired up, and 4 electrons would be alone. No, okay, so, all right. So it should be 4 electrons are paired up and 2 electrons are alone. So none of those are the correct answer here. So this is the best choice, but this is what the dot structure looks like. Sorry about that. All right, so let's move on to the next one. So here we got an orbital diagram, and they want to know what rules being broken. So we have all 3 basic rules that you need to know about. And so we're breaking one of those rules. So it's not written in here, but that's 1s, 2s, and then 2p, right? And a lot of people are going to think it's the Pauli exclusion principle or Hund's rule, okay? But the real one here is the opt-out principle, because this electron And the 2p1 here should be here. It should be 2s2 instead of 2s1. This electron is in a slightly higher energy sublevel than what it should be. So remember, off-balance principle says the electrons have to be in the lowest possible energy levels and sublevels as possible before they go to the next energy level. So this electron should be here, and it should be a down arrow. But the rule that's being broken is the off-balance principle. Okay. So let's go back to the test. All right. So they just ask us, they give us the volume of a solution, they give us how much chloride we have in it, and it asks for molarity. So we just have to remember molarity is moles over liters. So we're going to have to convert this to liters, and we're going to have to convert grams of chloride ions to moles of chloride ions. Okay. And we got to be careful here with the chloride because we're used to seeing chlorine as Cl2, but this is chloride, which is just one chlorine. So don't double the molar mass, right? So chloride Cl would just be 35.45. It wouldn't be doubling that because it's not Cl2 here. So we would divide by the molar mass of chloride to get how many moles we have, and then just divide by liters and not milliliters to get our molarity. Okay. All right, let's keep on going here. All right, so we have an element and it gives us three isotopes and their mass numbers. So 121, 124, and 125. And then they give us the average atomic mass. And notice the average atomic mass is closer to 121 than it is to 124 or 125. So what does that mean? It means 121 is the most abundant. Okay, so that's the most common isotope, and these would be more rare. Right? If the number was closer to 125, then maybe 125 or 124 is more abundant, right? Just kind of depends, but remember it's a weighted average. And whatever one of these numbers it's closest to, the average atomic mass, whatever it's closer to, that would probably be the most abundant one, okay? Number 27, what products will form when aqueous solutions of sodium phosphate and lead 2 nitrate are mixed? So just double replacement, predicting the products, using your solubility rules. So hopefully you know that sodium nitrate would be soluble. So choice D would be incorrect because that's not going to precipitate, right? And choice B is incorrect because, again, that's not going to precipitate. And we know that it's going to be the lead phosphate if we look at our solubility rules. Again, you have them on the back of your periodic table. We know that's going to precipitate, so that's not going to be aqueous. So choice C should be the correct answer there. Okay, so the lead 2 phosphate is going to precipitate, so it'll be a solid, and the sodium nitrate will stay dissolved. It'll be aqueous, right? All right. So here they give us the dot structure, and they just ask us for the shape and if it's polar or nonpolar. So remember, first off, remember boron is okay with 6 electrons, so this is perfectly fine for boron. This is what the boron trifluoride molecule could look like if you draw it. It's not really drawn well based on its actual geometry, but that's a perfectly good dot structure. We should understand that because there are no lone pairs on the boron, and these things coming off of the boron are fluorine, and they're all the same. This is a symmetrical molecule, so it's nonpolar. So we could eliminate answer choice C, and we could eliminate answer choice D because we know it's nonpolar. Okay, it has polar bonds, but it's a nonpolar molecule. If they ask us about bond angle, be careful. If they ask us, like, if they just said, hey, what's this bond angle here? Don't say 90 for that one. And then if they ask you that bond angle, don't say 180. Okay. But it's asking for the shape. And when you have 3 bonds, 0 lone pairs, that's trigonal planar. So the answer is B, trigonal planar, and it's nonpolar. If it asked about the bonds, it would have polar bonds, but the molecule itself is nonpolar. Okay. All right, so number 29, it looks like we got a half-life question. So they give us a nuclear decay chart, and I guess we could figure out the half-life here. So to go from 80 to 40, It took 2 days, so the half-life is 2 days, so it cuts in half every 2 days. So basically, we want to know how long it's going to take to go from 1,200 grams to 37.5 grams. So, we could use an equation, or we could just do it the easy way. We'll take 1,200 and we'll divide it by 2, and we'll keep dividing what we get by 2 until we get to 37.5. And the number of times we divide by 2 are the number of half-lives, and each half-life is 2 days. So if we start with 1,200 and we divide by 2 and we keep going until we get 37.5, we have to do that 5 times. All right. So 5 half-lives, a half-life is 2 days. So 5 half-lives occur. It's going to be a total of 10 days. All right. And remember, we'll only deal with whole numbers of half-lives, so we don't have to really worry about the logarithmic half-life equation. Okay. All right. So number 30, and this is where we'll stop this video after number 30, and we'll finish up in part 3. Okay, so how many molecules of CO2 can be created when 250 grams of butane, and they give us the molar mass of butane, burns in oxygen? So just a stoichiometry problem. We don't have to worry about running out of oxygen because we have excess oxygen. So what are we going to do? We're going to take our grams of butane, divide it by the molar mass that they give us, and that'll convert to moles. Then we're going to multiply by the mole ratio. So we want to know molecules of CO2. So once we get moles of butane, we're going to multiply by 8 and divide by 2. Or we're just going to multiply by 4. And then that'll give us moles of CO2. And then once we have moles of CO2, we're going to have to multiply by Avogadro's number. Now, hopefully, if you're going to guess a number of particles, you're not going to guess 1,000. That's not enough. And you're not going to guess 17.2, right? So hopefully you could eliminate answer choice A and answer choice C as possibilities, because they are not possible. All right, so we're going to go with... if we had to guess, it's either going to be this one or this one. It's only going to be this one, if we're multiplying Avogadro's number by 10 a couple times. So probably not this one, but let's, do the math. All right. So we take our 250 grams of butane, we divide it by 58.14. Multiply it by 8, divide by 2, or just multiply by 4, and then multiply by Avogadro's number, and that's our answer. Okay, so it came out to be answer choice B. Okay. All right, so we'll finish this up in the next one. All right. Good luck reviewing.